Hello everyone, let's take a look at our next problem. The equation 8 to the x plus 4 equals 4 to the x plus 2 to the x plus 2 has 0, 1, 2, or 3 real solutions. So my first thought is we're working a lot with powers of 2 here. I might want to write everything in terms of a power of 2. And then we might treat this as a quadratic equation or a cubic equation with respect to 2 to the x. And just sort of try and solve for 2 to the x first, see how many different values there are of 2 to the x, and then solve for x from that. Let me write everything first in terms of the number 2. So this looks like a cubic equation with respect to 2 to the x. Let me rearrange things and show you show how that's what's going on there. So I've just rearranged what we had in the line above, and we see now that this is a cubic equation with respect to 2 to the x. So we've got to figure out how many roots this equation has. Let me write this as y cubed minus y squared minus 4y plus 4. Let's find out how many roots that has. And if there's any positive root to this, then if I find a positive value of y, which satisfies this, then there will be a real root in terms of the x equation. But any root of this equation which is 0 or negative will not have a corresponding real value of x that solves it. So for a cubic equation, how can I figure out how many roots this thing has? Well, if y is equal to 0, like I think the best way to do this is to think about a plot, right? Think about think about what this cubic thing looks like as a function of y. So when y is equal to 0, this thing is equal to 4. And as y goes to infinity, this thing will go off to infinity. And when y, we're not really concerned with negative values of y because of a negative value of y will not give us a real value of x. But we know that when y approaches negative infinity, the graph of this will go off to negative infinity. Okay, so we know that we have, starting from here, the function is decreasing at this point, certainly, and that comes from the negative coefficient on y, right? So if I took a derivative of this and then set y equal to 0, the derivative here is negative 4, so it's decreasing like this. And it's going to turn around once. There's only going to, so it either looks like this, or it does dip below and it looks like this. So I got to figure out which of these two cases occurs. And what I'm going to do is I'm going to take a derivative of this and set it equal to 0 and then solve for y, because that will give us the value of y for which this thing turns around, right? It'll give us the minimum value. It'll give us the value of y which minimizes this curve. Once I have that value of y, I'm going to substitute it back into this cubic and see whether the value of the function attained is positive or negative. I've thrown out the negative root, or the negative value of the square root, because that is going to give us a negative value of y, which we're not concerned about. So this is the value of y where the function turns around, or it has a local minimum at this place. So now I want to figure out whether I'll call this y star. I want to figure out whether f of y star is positive or negative. This looks like it's going to be kind of messy, so I'm going to think for a second whether there might be a more convenient way to look into this. I might be able to do some factoring of this thing on the left-hand side. So I'm going to take a brief detour. I'm going to put a little asterisk here next to that computation. I might come back there. But let's look at the original cubic expression. Okay, so this is quite a bit easier because we can explicitly solve for all the roots for values of y here. So we have y minus 2, y plus 2, and y minus 1. So the roots of this cubic are 2, -2, and 1. The ones I'm concerned with are 2 and 1 because remember that y is equal to 2 to the x. So I have x1 is equal to log base 2 of 2, which is in fact just 1, right? And I'll call it x3 just so the subscripts on x's and y's match. But this will be log base 2 of 1, which is 0. Okay, so let's just check that these are in fact solutions, 1 and 0, to the original equation. If I plug in 0, on the left I get 5, and on the right I get also 5, so that works. And if I plug in a 1, on the left I get 12, on the right I get 4 plus, I get 12. Okay, so those two values of x, 0 and 1, are roots. But the analysis that I did shows that there can't be a third real solution, right? This cubic here, one of the roots of this cubic is negative. And so let's in fact, we know it's -2, right? 2 to the power of x can never be equal to -2 for a real value of x. So not only do we show that there are two real solutions, we actually know what they are. Yeah, so this was, this ended up being a good example, which shows that, there may be more than one approach to solve a problem, and sometimes some approaches are a lot easier to work with than others. I simply didn't recognize immediately that this thing could be factored easily. My mind instantly went to, well, I've still made the substitution here that y is equal to 2 to the x, and treating this as a cubic equation in y. But I didn't see that this could be factored right away, and I was just kind of looking at, I suppose, call it the geometry of the graph of this cubic function, and trying to argue from there. Yeah, nice problem. If I have any more comments or if I find some kind of error, I'll put it in the description below. Otherwise, thanks for watching.